heat transfer mechanisms. So let's go to okay. Let me get this. Okay. So we're looking at heat transfer mechanism. Okay, the first week we looked at energy balances, and we saw that they are so insightful. And it's just a balance of energy, and we talked about energy stored. We did not say how the energy is moved from one place to the other. That's what we're doing this week. And the way we're looking at how the energy moves this week is by looking at the formulas, right? The mathematical expression of the different mechanisms. We're not getting into their physics, although we will do that in the second half of the class. Right now, all we know is that if we have convection, we have two different types of convection, natural and forced. In all cases, the formula to calculate heat losses by convection was that the heat flux is a proportionality coefficient H, which we call the heat transfer coefficient, times the difference in temperature between the surface and the fluid far from the surface. We did that. We looked at radiation that to some extent was similar, except that instead of being a delta T was T to the 4 of the surface minus T to the 4 of the surroundings. And it had some coefficients too, like the Stefan Boltzmann coefficient and the emissivity. Then we looked at what happens if we put two bodies of different temperature in contact. And we saw that there is like a resistance to the flow of contact, and the heat flux across that resistance we could capture with something that looked much like the convection coefficient, right? Times the difference in temperature between the interfaces. We also saw that in the case of radiation, by doing this little trick of expanding the difference of squares, we could come up with an equivalent coefficient of convection, but in reality was for radiation, right? The physics are very different, but the mathematical expression ended up looking very, very similar. And although the mathematical expression looked very similar, the trick was that in convection, H is more or less constant with temperature, but in radiation, H varies quite a bit. The H of radiation varies quite a bit with temperature. And then we start to discuss conduction, and that's where we are getting now. We said in conduction we have Fourier's law, and Fourier's law was had this expression in the form of a derivative. And what is new about conduction? Conduction happens inside a body, while convection, radiation, or contact, they all happen through surfaces. In this case, contact, in this case, conduction is inside. And there is another difference. While the other heats we have discussed so far come out of the surface, in the case of conduction, it has three directions in which it can move. It's actually a vector, right? So in this expression we have here is the heat flux by conduction in the x direction. And we mentioned this minus sign is very important because it says that heat moves in the direction that the gradient decreases. That's a fancy way of saying heat goes from hot to cold, which we all know. But this is the expression here. We did an example and we saw that heat conduction in metals is very fast, much faster than, well, under the conditions we consider was faster than convection or radiation. Then we extended this very simple formula that came from an analysis of things people have seen, and it was quite intuitive. We said, okay, let's replace this one-dimensional gradient, which is a derivative, by a 3D gradient. And here we have the expression. So now heat, instead of being this heat flux that is a scalar, is a number, now it becomes heat by conduction, it becomes a vector. And this is the gradient in 3D. And in rectangular coordinates has this expression, and in cylindrical coordinates has this other expression that it comes from doing multivariate calculus. And we're not going to worry about how we landed here. We'll just take it for granted, but this can be proven. This is exact, right? And if you see these two gradients look somewhat similar, but they're not quite, right? These ER, E phi, EZ are the unit vectors in the radial direction, in the tangential direction across the polar coordinate, and in the longitudinal direction of the axis of symmetry. Well, and the axis of the cylindrical coordinate. And look, there is a 1/r here. And r is the radius measured in the plane XY plane. In spherical coordinates, things have some similarities. A radial unit vector in the radial direction, but now instead of having a longitudinal coordinate, right, Z, we have two angles, right, the azimuthal and the polar angle. And we end up with this kind of crazy expression. And if you look at the book that I highly recommend you get, you see how these angles play. Then we said, okay, all this math, what was the point of all this math? And the point was that these complicated formulas can actually help us have very simple formulas under some special cases. There are three cases we will discuss. One of the cases is when we have symmetry. So when we have symmetry of revolution in cylindrical coordinates, this 3D gradient turns into a 2D gradient. If you're doing some computer simulations, that makes you very happy because it makes your life a lot easier and your calculations a lot faster. And if you're in spherical coordinates and you have spherical symmetry, as you very often have, your 3D gradient has symmetry in two of these angles, and your 3D problem of a sphere, which is very 3D, becomes a 1D mathematical problem because you have only one variable, only one independent variable. So that's the reason why we look at these coordinates. And for most of the class, we're going to be looking at plates, cylinders, and spheres. If you want something crazy, we can do it, but you have to do it numerically, doing finite elements or finite differences or something like that. And in some cases in which you have geometries that are like well-defined, such as ellipsoids or paraboloids, people have developed coordinate systems for that, which we don't teach here, but with which you can say, oh, if I have an elliptical symmetry, then your problem becomes very easy again, but you just needed to change the coordinates. That sometimes is time-consuming still. So symmetry is one of the ways in which we can simplify a problem of heat conduction, whether we have cylinders with cylindrical symmetry or spherical symmetry. There is another conduction, another situation in which we can simplify our heat conduction equations, and this is not exact, but it's a good approximation, and it's when the geometry has some special conditions. Typically, when something is very long and thin or very wide and flat, in those conditions, typically we can neglect a variable. I want to show you just one example of this. So let's consider the heat exchange, the fluid losing heat in the tube of a heat exchanger. This is only an example. This, I'm going to tell you, would apply to the analysis of fins on a BMW motorcycle engine that is air-cooled. This would apply to a hot cable, for example, in welding, or the cables that cause fires in houses, in which the electricity causes heating in the cable and is losing that heat to the outside. So let's look at this control volume we made here. We have the heat exchanger tube, and we have fluid going in. I'm going to pick an Eulerian coordinate frame. That means the coordinate frame stays quiet, but the fluid goes through it. And let's say, for this example, that the surface of the tube is constant. Right? There are different conditions which we're going to see. This is a condition that is realistic, but in this case, I choose it because it's going to make the same explanation be a lot simpler from the point of view of math. So we have to use our imagination. Heat exchanger has tubes. These tubes, let's say the tube is at the same temperature. The tube, anywhere I measure the tube is same temperature. But I put a fluid, and let's say that the fluid is a hot fluid. So that means hotter than the tube. The fluid is going to start hot at one end of the tube and it's going to cool down at the other end of the tube. So in this schematic, we see how the temperature in the center of the tube is going to be cooling off as it goes into the tube. I put hot fluid into a cold tube. The fluid is going to be cooling down. We all know that, right? In addition to that, we have that the fluid that was hot and is in contact with a cold tube is going to be hotter in the center and colder at the edges because the fluid is getting cold in contact with the tube. So we have, in this case, if we talk about cylindrical symmetry, we have a 2D problem. We have temperature that is changing in the longitudinal axis, and we have temperature that is changing in the radial axis. So one of the boundary conditions is that two things in contact, in the case of a fluid in contact with a solid, there's no contact resistance between fluids and solids. I should add that up to the notes. I'm gonna do it now. Okay, so if there is no contact resistance, the fluid has the same temperature of the surface of the tube, right? And so all over here, all over this wall, the fluid has the same temperature of the tube. In the center here, the fluid is hotter, and we would have this profile we see in AA. As the fluid goes down, the surface, the fluid that is in contact with the surface is always at the temperature of the tube. But the maximum temperature of the center is going down and down and down. Eventually, the whole fluid is going to be at the same temperature of the tube, right? Okay. Now let's do a little bit of an analysis. Heat transfer by conduction is proportional to the gradient. That's what Fourier's law tells us. Right, it's proportional to a gradient. And in the case of cylindrical symmetry, we see that the vector of heat transfer by conduction has a component that is radial with a radial gradient and a component that is longitudinal with a longitudinal gradient. So heat transfer, in this particular case we're talking about, a fluid inside the heat exchanger, will have a component of conduction that is longitudinal, because we have hot fluid on one end and colder on the other end, there will be some heat flow, and another component that is radial. So let's assess these two components of gradient, right? These two components of heat transfer by conduction. Radially, we could say, and this is an approximation, I can do a lot better than this because that was the topic of my PhD thesis, but let's spare all that beauty. I'll be happy to discuss with any of you interested, but yes, we can say that the radial gradient is more or less the difference in temperature between the center temperature and the surface temperature divided the radius. That's more or less what the gradient is. And you see, the issue is not so much the math here, is what this math means. Longitudinal gradient, similar story. I start at the center with a high temperature, and at the end, eventually everything is in equilibrium. So I would have a temperature difference that is more or less the same delta T, same difference in temperature between inlet and outlet, but in this case divided by the length of the tube. Now, some of you have seen heat exchangers. Some of you have not, but you can imagine them. And in all cases, you know that the tubes are way longer. They are much longer than they are wide. So L is much bigger than the radius. And in that case, let's see if and in that case, this gradient in Z, the longitudinal gradient, is much smaller than the radial gradient, because in this case, I'm dividing by a long number, that is the length that can be meters. And in this other case, the radial case, I'm dividing by a small number that can be centimeters, millimeters, right? And so in a heat exchanger, because of it, the tubes are long and narrow, the geometry is such that the heat loss, the heat transfer by conduction is almost completely radial, and the longitudinal part we forget. As you will see, every time we talk about heat exchangers, we're going to forget about the longitudinal aspect of conduction. This is one of the reasons. This reasoning I just did would apply not only to heat exchangers, would apply to fins in which we have no fluid moving in, a fin is solid, would apply to the cables, right? So all that matters here is that the geometry is such that something is long and something is big and something is small. In this case, diameter is small, length is large. If we have a fin, we can say the thickness of the fin is small and the length of the fin is large. And this would apply. This is an approximation, it's not exact, but it's an approximation that is so good, we're going to be doing all the time. For those of you in MATI, when we do calculations about welding, the heat transfer on the plate is much broader than thicker. So we apply this condition, and the heat losses by convection, we consider they are all in the radial direction and not longitudinal. Very interesting. If you take the heat transfer, the welding class, you're going to see more about that. So let me see. Okay, I want to discuss a third consideration. First, we discuss symmetry, that is exact. If we have symmetry, our equation simplifies, and that's exact. Then we talked about simplifications based on geometry, in which if something is big and something is small, we're going to say that the small part is negligible. That is not exact, that's a lie, but it's a pretty good lie because it helps you have a much simpler calculation and your cost inaccuracy is very small. Typically, the cost inaccuracy of your calculations is a smaller error than the error of measuring what you're doing. And if you cannot measure, you don't even know if you have a small error or not. I want to discuss a third thing that is a consideration based on the physical consideration. This is another approximation. It's another amazing approximation. So just before, we neglected conduction in the longitudinal direction because conduction in the radial direction was so much bigger. But in addition, in this same problem, and I chose it that way, we have another effect. We have the effect of fluid moving. In a fin, you don't have any fluid inside the fin, but in the case of the heat exchanger, you do. So now you would have heat transfer by longitudinally. You can have heat transfer by conduction, but you also would have heat transfer by advection as we move the fluid. So are there cases in which conduction dominates, or are there cases in which advection dominates? Let me tell you right now that in heat exchangers, advection completely dominates. Why? Okay, so I'm going to go about this twice. Once I'm going to do now in a simple form, and I think not next week, but the week after, we're going to be discussing differential control volumes, and we're going to do it rigorously. But let's look at this. We go back to this example, the fluid inside a tube of a heat exchanger. And we already said longitudinally, the heat loss by conduction would be, right, the cross-sectional area of the fluid times the heat conductivity, the thermal conductivity of the fluid, times the difference in temperature between the inlet and outlet of the tube divided by the length. This is what we had already seen. Now, there is something else we have already seen that I want to bring to the conversation is the heat losses, right? The heat by advection is the heat that is lost through the surface of the tube. We're not saying right now how the heat is lost, but we say it is lost. Typically it's by convection, but could be a radiant tube, could be so many things. So the heat rate by advection is that of the heat loss, and we had already seen that. We saw that in our first week of class. And in the first week of class, we saw that at the beginning of Monday, because we didn't finish it in the first week. We saw we had this expression that is mass flow times specific heat, in the case we have no phase changes, and times the temperature difference between the inlet and the outlet. And of course, the mass flow we can express in the form of volumetric flow times density, and volumetric flow is cross-sectional area times some velocity. We will learn exactly what velocities to use, but there is some velocity of the flow that we already know. If I make the ratio Q of heat by advection divided by heat by conduction, right? When this ratio is high, that means heat by advection dominates. When this ratio is small, it means heat by conduction dominates. And look at this. If I do this equation 22, that is heat by advection, divided equation 21, that is heat by conduction, these temperature differences cancel each other out, right? The cross-sectional area cancels each other out. And I end up with this 22, equation 22 divided equation 21, is equation 23. This is dimensionless, right? Because this is watts divided by watts. This is dimensionless. this part here, these three things together that says rho Cp over K, okay, K over rho Cp appears all the time in heat transfer, and it has a name. K over rho C is thermal diffusivity and has units of meters squared per second, same units of any other type of diffusivity. So one thing to know, we're going to be using this parameter alpha a whole lot. And alpha is not coming out of nowhere. It's a combination of thermal conductivity and specific heat and density. All right, so this ratio would be UL over alpha. Because we use this a lot in heat transfer, we give it a name, and we name it the Peclet number. And the Peclet number is a ratio between the heat rate by advection divided the heat rate by conduction. High Peclet number means advection dominates. Small Peclet number means conduction dominates. In heat exchangers, the Peclet number is of 10 to a big number, is huge. So we don't worry about conduction. If the fluid is moving extremely slowly, then we can forget about advection. We can have other effects like geometry effects or symmetry effects. But advection matters when the Peclet number is high. This I just explained is not explained well in the book. And it should, because it's a very important concept. When fluid is moving, who wins? The heat transfer by conduction or the heat transfer by motion? Now you know. You calculate the Peclet number and you give me a straight answer. You look at Peclet. If it is bigger than 10, typically we say advection dominates. If it is smaller than 0.1, we typically say conduction dominates. And when it is between 0.1 and 10, we're kind of in a mixed regime in which both heat transfer mechanisms are comparable. Super cool. This is powerful, very powerful. So I'd like to wrap this up, is an example of real life that puts together the things we have seen so far. So, and it's about thermal balance in humans. So this is an elaborate example. It's all written down, but it helps you see some interesting things. So let's talk about an average woman that consumes about 2,000 calories per day. Those are the calories you eat. It's like when you buy food and it says so many calories, those are the calories I'm talking about. You see that I use calorie with a big C. That actually is a funny thing. Is not the scientific way of writing, but that means 1,000 small calories with a small c, right? So we know that in average, humans lose about 600 grams of water per day due to like exhalation and perspiration, right? So we lose water. As I'm talking to you, I'm losing water, right? At the end of the day, I lose a little bit more than half a liter of water just from being alive. I'm talking so much that I'm losing more than that. Also, we know that the average surface area of a woman is 1.6 meters squared. For a man, it's a little bit more, right? And we also know that although our body temperature is about 37 degrees, the skin is a little bit colder, and in average is more or less 33 degrees C. All these things we know, right? If you go like to papers, there are lots and lots of information about human bodies. So the question here is, how do these things that we know, especially the eating 2,000 calories a day, relate to our thermal balance? And before I do any numbers, I'll tell you the end. The amazing thing is that we eat 2,000 calories per day because we lose 2,000 calories in heat during the day, right? Isn't that amazing? Is that like what we eat is just to keep us warm? So let's do a thermal balance. and see what mechanisms are associated. So although we don't have it here, let's see. Let's see if this works. All right, so oh my God, this is ugly. Here. Much better, huh? So I hope I don't get sued for this drawing of a woman I'm doing here. Ooh, maybe I will. No. Okay. It's a pretty sad woman. It's probably the effects of COVID. So, and here we do our control volume. And in this control volume, we're going to have some heat out, right? Q out. That would be Q of convection plus Q of radiation. And also, we are going to have an amount of mass out, that is the mass of water that is evaporated, right? Plus so we have Q in, let's say there is no heat coming in. Let's say this is surrounded by an environment at 20 degrees C. The surface of the skin, we said, was 33 degrees C, right? And let's say Q in equals 0. Let's say we're in steady state, in which this lady is not getting colder and colder and colder, or hotter and hotter and hotter. So if it is in steady state, Q stored equals 0. Now, in this case, our lady friend is not radioactive, but it does have heat generation inside. That is the metabolic heat, right? Q generated is the metabolic heat. And that is the 2,000 calories per day we need to eat. So now we can put all this together, and we would see that let's go back to our transfer mechanisms here. All right. So let's look at first, let's look at the losses by evaporation. And we know, okay, here I have heat generation. Heat generation, we have to do a little bit of a unit conversion. I used to ask people to remember these numbers. I don't anymore. You can Google them. I don't need to worry about that anymore. If you look at the old formula sheets that are uploaded, I have these unit conversions there. And one big calorie with a big C means 1,000 small calories, and one small calorie is, give or take, 4 joules, right? So 2,000 calories per day is just shy of 100 watts. So first interesting thing to know, just being alive, we're burning 100 watts. That's women. Men are about 2,500 calories, so it's a little bit more, 2,500 calories per day. That's a little bit more, right? That's actually quite a lot of heat. And that's the reason why if we're in a packed room, it gets so hot. Every 10 people, we have 1 kilowatt of energy, thermal energy being generated. It's a lot. All right. And much of that is used by our brain, right? So we have a sense of about our power. We run on 100 watts. So that is the Q generated. If I compare the Q generated with the, if I compare the Q generated and I said with the heat by convection and evaporation, the heat by evaporation, we have seen in our example of boiling pasta, we have a mass flow, right? And this mass flow is 600 grams per day. And we know the enthalpy of the vapor coming out. We did this example before. And what this says is by the energy we lose by this advection through our control volume, right, is of the order of just almost 16 watts. So we eat almost 100 watts, we lose almost 16 watts in our breathing and in our perspiration. The rest would be a combination of radiation and conduction and convection, radiation and convection. And when we have radiation and convection together, we would use this all right. When we have radiation and convection combined, we would have this H effective, right? That had the convection equivalent for radiation. We know the area, we know the temperature of the skin, the temperature of the surface, we know the temperature far from the, we know the temperature of the fluid, that is 20 degrees for air in the room. And then we can solve. If I know that what the heat I'm losing is by radiation and conduction, and radiation and convection is about 80 watts, right? And I can have these 80 watts, know the area, know the temperature difference. I can solve for the convection, the effective convection coefficient. And I get a number that is kind of 4, right? This is amazing because in this very simple calculation, we got to see that an average woman loses heat with more or less 4 watts per square meter per Kelvin through her surface. Now, what number we would have expected? Well, we said natural convection is more or less 10 watts per meter square Kelvin. We said radiation near room temperature is of the order of 5 watts per meter square Kelvin. So very ballpark, I would have expected 15. And our calculation gave us 4. So what happened there? 2 things happened there. Number one, when I said 10 and 10 watts per meter square Kelvin is very ballpark. We're going to do calculate, that is, this 10 is a round number that is easy to remember. We will learn how to calculate this properly, but 10 is kind of right. The radiation was 5, that was quite okay. So we have 15. So I know that it should have been 4. We calculated, we expected more or less 15. Number one is when I rounded up to give you a round number of 10 watts per meter square Kelvin. But there's something more important. Let's assume our lady is actually with clothes on. And clothes, oops, here, clothes are thermal insulators. You know, because a jacket is a thermal insulator. And you know that how much of a benefit it is when it's cold or windy to have your clothes on. So the difference is in part for the round-off, the rounding error in the data I gave you. And the other part is because we did not account for the thermal resistance of clothes. We will learn lots about thermal resistance very soon. In the, I think will be the 5th week of classes, right? So what is the conclusion from this problem here? Number one, 2,000 calories is what you burn just by being sitting, right? And that's why athletes that burn a lot of energy doing exercise need to eat more. But it's not true that if you do no exercise, you need 0 calories. No, just being alive, your metabolic heat is at a minimum of these 2,000 calories. That's a really cool thing. Number two cool thing is I have given you some very simple formulas, and I have given you some very rough numbers that should be easy to remember. We're going to do those numbers much better later, but you already have some ballpark numbers. And just based on that, you're able to anticipate things of real life. And this is the reason I asked to teach this class, because I love it so much. The fact that I can make sense of my everyday life, not to mention I can make sense of industrial equipment using these few simple concepts and putting them together and building a cathedral of knowledge brick by brick with these things. Good. In these 5 minutes we have, I'm going to switch to start discussing our next topic, that is lumped capacitance. As I switch, if you have questions or comments on this topic, please put them in the chat, and I'm going to be paying attention to that.